We are group 15, and this is our final project presentation for AER. And our discussion is on the Ivanpah Solar Electric Generating Power Facility, including a SWOT analysis and a feasibility discussion. So firstly, just some background on the Ivanpah Solar Power plant. It's a concentrating solar thermal plant located in the Mojave Desert on the California-Nevada state line. The gross capacity is about 400 megawatts, and the average annual output is about 856 gigawatt hours. It has 174,000 heliostats, which are aimed at 3 solar power towers equipped with boiler. In this case, the working fluid is water, although you can use molten salts in these systems as well. Water is pumped to the tower. It's vaporized at usually a high pressure steam header condition, greater than 60 bar and greater than 550 C. And then the steam is fed to a turbine to generate electricity. And you can see a schematic of a typical plant on the right, where the heliostats heat the receiver, and then the steam flows down to the turbine, and the water is recycled through a condenser. It was constructed in 2010 and commissioned in 2014. The current capacity factor is about 24%. They license BrightSource Energy's Lutz Power Tower technology, and they also use Siemens SST turbines for the control systems and the turbines. The total cost was about $2.2 billion. And interestingly, the facility received a $1.6 billion loan guarantee from the US DOE, and their contract states that they sell 2/3 of the power to Pacific Gas and Electric and the remainder to Southern California Edison. The irradiance is great in the area at about 7.4 kilowatt hours per meter cube per day. And overall, the plant has been operating successfully. It burns natural gas in the mornings to start up. There are some issues surrounding endangered species, specifically the Mojave Desert tortoises, and also there have been controversies over birds, which will be discussed later. On the right, you can see the 3 power towers of the Ivanpah facility, all glowing. The turbines are located right next to the power tower, and the heliostats are surrounding on the ground below.
Yeah, thank you for that introduction, Jonah. I think another good place to start would be to talk about the different types of solar thermal technologies, in particular linear concentrating systems and power towers, because it'll help motivate the pros and cons of Ivanpah a little later on. Ivanpah mainly uses power tower, which I'll get into in the next slide, but let's first talk about linear concentrating systems. So linear concentrating systems have 2 subcategories, parabolic troughs and Fresnel reflector systems. So what these 2 subcategories share in common is that they capture the sun's energy with very long mirrors. And these mirrors span the length of tubes that receive the light. And there's liquid inside the tube that gets heated up and sent to some kind of generator to be converted into electricity or electric energy. And so to get these to work on a large scale, you have to use very long tubes. As a result, as we can see in the case of parabolic troughs, they will concentrate light to 30 to 100 times more its original intensity. In contrast, we have Fresnel reflector systems where they have a similar concept with the receiver or the reflectors concentrating light onto a receiver. But the way these reflectors do that is making use of something called the Fresnel lens effect. The Fresnel lens effect is a bit out of the scope of this presentation because, as I mentioned before, Ivanpah uses power tower, but it's worth noting because this method can concentrate light up to 30 times more its original intensity while also saving costs. It saves costs by reducing the amount of material in the design of the lens itself, which makes it much less expensive than parabolic troughs. Next slide. And so while power towers and linear concentrating systems both make use of mirrors that track the sun and capture light onto a receiver, the main difference between them, as the name would imply, is that this receiver is instead at the top of a tower. So it still takes quite a bit of time and resources to construct, but the light can concentrate up to 1,500 times its original intensity. Another potential difference is the heat transfer fluid. In the case of Ivanpah, it's still water, but those who are trying to advance power towers have been experimenting with molten nitrate salt. It's a good heat transfer fluid, and it has storage power, which is especially helpful for days where it's not as sunny, or at nighttime where the sun isn't even out. And so this also relates to another kind of solar thermal energy, sort of a bonus or an honorable mention. honorable mention because there aren't any utility scale ones in the US right now, but that mainly has to do with the lack of storage power because the receivers collect heat and transfer it into a Stirling engine. And because Stirling engines produce electricity directly, it lacks that storage capability. But it still works similarly to parabolic troughs in the sense that there's a solar dish with a sort of curve that that's covered in mirrors and sort of directs the sunlight onto a receiver to, you know, collect the heat and all that. Next slide.
Thank Fatima for the introduction for technologies of power generation. So here comes to the power tower versus parabolic troughs, pros and cons. So compared to the parabolic troughs, here are the advantages of power tower over troughs. First, towers can produce up to higher temperature, higher pressure, and higher concentration ratios, leading to higher efficiency and less energy cost. And we use less piping in comparison to trough, which employs many kilometers of pipes to transfer the heating fluid, resulting in heat losses. Also, we use flat mirrors in power tower, which are cheaper than parabolic trough mirrors. And there is less energy loss because the power tower produces steam directly and not through a heat exchanger, minimizing energy loss and maximizing plant efficiency. However, there is still limited commercial experience with most of existing solar thermal plants using trough. As for the parabolic troughs, although there are many proven operation track records and employs single-axis trackers, but there is relatively low thermal to electricity efficiency, and the curved mirrors are more expensive. We need to consider the durability of piping. Next slide. As for the cost comparison, first, capital cost. The power tower investment range is about $3,300 per kilowatt to $6,200 per kilowatt. However, for the parabolic trough investment range is $4,200 per kilowatt to $6,200 per kilowatt. The capital cost varies in install cost, power cycle cost, balance of plant cost, and thermal energy storage facility cost. Next slide. As for the operation and maintenance cost, operation and maintenance costs for concentrated solar power plants in operation today range from $0.02 to $0.04 per kilowatt hour. Given differences in radiation plant design, technology, labor costs, and individual market component pricing, operation and maintenance cost varies from location to location. So here is an example which we can use as a reference for cost comparison. So here you can see the levelized cost of energy is about $11 per kilowatt hour for solar power module, while for the physical trough module, the price is about $15 per kilowatt hour. But it is still very difficult to make an exact comparison between towers and troughs because the plant's nominal power, size of heliostat field, and storage capacity depend on its location and defined dispatch profile. So next one.
So here comes the environmental impact. One of them we should take into consideration for this specific solar thermal plant is light pollutant. Impacts of glint, glare on eyesight can include discomfort, disability, visual effect, and so on. And besides, except for the impact on the ground pedestrian, another major influence of the glare emitted by Ivanpah is on the plant flight. And there are already pilots complaining that they could not look into the solar plant direction due to the intense brightness emitted by the heliostats in standby mode as they departed from the border city of airport and climbed southwest. And next one. The second environmental impact we need to concern about is consequential ecological impact leading by taking up the land even in the desert. Actually, Ivanpah is a good example of taking up low quality land in the desert. The local ecosystem has suffered a lot because of the plant. One of the most significant examples is desert turtles. Ivanpah project encroaches on land that the desert turtles has called home for millennia. Actually, many human activities will damage the local ecosystem, like military exercises, grazing livestock, and now this one, the solar thermal power plant. Since 1950, the turtles population has collapsed by 90%, and the idea of relocating nether turtles has cost over $50 million. And the next environmental impact need to be discussed is water use. Many of the regions in the United States that have the highest potential for solar energy also tend to be those with the driest climate. So careful consideration of this water trade-off is essential. For the Ivanpah cases, they use recirculating technology with cooling tower withdrawal between 700 to 900 gallons of water per megawatt hours of electricity produced. The water consumption is higher than natural gas power plant, which is below 300 gallons of water per megawatt hours. And the last one of the environmental impact is greenhouse gas emission. Even though the solar thermal power plant seem to be a renewable energy. During the construction phases and operational phases, the greenhouse gas emission is also a big issue. And the data is shown below, but actually this is the data from the feasibility analysis of the California energy emission before the construction of this plant. The actual number of the carbon dioxide emission of the operational year in the first year is actually double the ideal status. So the impact of whether it could be lower the carbon footprint is pending issue. So that's the environmental impact.
Thank you, Scarlett. Thank you, colleagues, for sharing that great information. Let's try and bring it all together in the market. I know what you want. You want to SWOT me. And this is our SWOT, starting with strengths. The cost of the CSP is growing closer and closer to PV and gas. We have a chart to the right-hand side of the slide, and you may look at that at first and say, okay, well, CSP is double what gas is. However, a couple of things. One is that in the final price to the consumer, it may be 25 cents per kilowatt hour. And at that point in time, this difference of 4 or 5 cents is less. It's still significant, but it's less. Also, the excuse me, pardon, if you add desalination to CSP, then you've got another stream of revenue, and that makes the cost less. My apologies for the sirens in the background. That's a different type of SWOT. So it has been discussed in Southern California, the Southwest, Arizona. I know people that, say, listen, clean water is a problem down there, so adding desalination is worthwhile. This is also going to be huge in the Middle East, where water is a serious problem. Desalination is a serious industry. Finally, there is one other ancillary, and that is that when you extract the water, desalinate, sometimes you get other precious minerals, and that would be a third revenue stream, which would bring down the cost even more. From its theory, it is zero carbon. Yes, there are other things like Scarlett mentioned, like the vehicles of the people getting there to go to work. However, we're starting from the best we can get, right? Certainly there are other ancillaries, but our starting point is as good as we can get. It also hybrids nicely with natural gas. The Ivanpah system works with natural gas, so natural gas can run at night while CSP runs during the day. You can run them both at the same time depending on the load, so that offers a lot of flexibility. With storage from CSP, it hybrids nicely with PV and wind, as you might imagine. The other thing that's interesting is that the PV, there's always PV at these CSP sites, and that electricity can run the heliostat and run ancillary pumps, etc. So you can supply the power to the plant from sunlight, from that solar, which is nice and direct. So excellent. Next slide. Weaknesses, as you can tell, the image says it all. It takes a lot of land. It takes a lot of land. We've been talking about this throughout the semester. It's a little bit less than twice as much as PV. The advantage we mentioned was the solar storage is a more natural fit. However, it takes a lot of land. PV is what people think of when they think of solar. And when I was looking at some of the subsidies in certain states, the subsidy, the tax code is strictly for PV. They've written in photovoltaic. They haven't thought of this possibility. The other thing that came up in my discussion with a gentleman working in this business is it's not macho like oil and gas. And while that doesn't sound very engineering-like, it does impact voters, and voters impact subsidies. So that's also significant. Weather dependency, no surprise. If it's raining out, cloudy day, you're going to have less irradiance. Now, these plants can work on gas all day long, but the whole point of this was to move away from gas as much as we can and use the sun. Next slide. Opportunities. Where are our partnerships? I mentioned that we hybrid nicely with gas and coal. A lot of these former coal plants have been switched to gas. They had all this land for the coal piles. Boom. That's excellent opportunity for CSP. There's also land for safety requirements. And I did look on Google Maps and looked at a couple of plants in Texas, and they do have space. They have enough to add another 30 to 50 megawatts from CSP. Engineering is simple to manage. That is to say, someone who can run a coal-fired or a gas-fired power plant can run a CSP plant. So the training is not specialized. It's also good PR. Listen, yeah, I've got a gas power plant, but at the same time, I'm running a lot off the sun. I'm getting that PR, even though my gas plant may not be running fully on CSP. So that's excellent as far as PR, but also excellent for CSP, and it's growing the market, growing in the market for itself. The more plants there are, the more installations there are, the better the margins can be. That is to say, the cost can come down. Virtual power purchase agreements are already in place. This is where if I live in Oregon and I want to buy clean power, clean energy, I can sign an agreement. It may be generated in Arizona and delivered in Arizona, but I'm purchasing that equivalent of clean energy for myself in Oregon off my grid. So this is already in existence. The current federal administration expects some subsidies. They are already in in discussion. They haven't come out yet, but much like previous administrations, we're going to expect to see subsidies like we saw before. Wall Street has money. No doubt about it. I've got some friends who work in this industry, and they specialize in renewables, and some even specialize in certain types of renewables. That's how big the market has gotten. And another opportunity is if we can get to higher temperatures, we don't necessarily have to generate electricity. We can treat or process other commodities, glass, cement, aluminum. So there's another opportunity for this technology beyond power generation. Next up. Threats. Yeah, who's that smiling face that's gonna stab us in the back? And I bring out the oil and gas lobby because I know that a few years ago, I was reading an article about Texas and the oil and gas lobby, which has its subsidies, and the renewables, it has its subsidies. They went after, the O&G lobby went after reducing the renewables. It was just straight up vindictive. It's a very powerful lobby, and it has to be reckoned with. PV gets even cheaper. That could be a threat. I mean, it does on the whole make solar in general, renewables, better. Price of natural gas could get cheaper. I will say from watching this back, one of my first jobs in the early 1990s was the gas bubble, and we are at a historically low price for natural gas, It's unlikely to happen, you know, just talking from the gut, but, you know, if I could predict the future, I'd have $1 billion and wouldn't be in grad school. So it could happen. Environmental press, we talked a little bit about this already. Migrating birds, for example, could fly in front of that very intense heat and barbecue dinner. So, right, the activists don't like this. We talked about the turtles before. So yes, this is part of the balance that we have to find. I'm going to pass it on over to Jonah.
Thanks, Martin. Some conclusions for our study. Overall, we found that solar thermal facilities are an attractive and promising method. Power towers show advantages relative to power troughs, namely in concentrating ability and scale for higher pressures and higher temperatures. The relative cost of each is similar from an installation perspective. However, data suggests that power towers are the clear choice for at-scale generation. Our SWOT analysis showcases that the cost is comparable with similar size fossil fuel facilities, and that is expected to continue to drop. The use of existing and working knowledge of gas turbine plants allows for hybridization of these facilities. There are extensive opportunities ahead. Projected increased subsidization via the current administration gives good signals ahead. Technology is robust and widely applicable to other industries. If we can get that temperature higher, we could apply this to cement, aluminum, gasification, carbon capture, you name it. However, land usage is a clear weaknesses and challenges lie ahead, specifically with lobbying and ecological concerns. Thank you for your time, and that was our presentation, and here are our references.